The topic of Chapter 19 is flux and flux integrals. Flux measures how much of a vector field passes through a surface. So the idea is this: if I have a surface and it's inside some vector field, then I want to measure in some way how much of this vector field goes through the surface. So just as a special case right off the bat, notice that if I have a surface and everywhere the vector field is in exactly the same direction as the surface, then none of the vector field passes through the surface and the flux would be zero. Whereas if the vector field is always perpendicular to the face of the surface, then I'm going to get a large amount of flux. Okay, so a good way to think about flux is to think about a river and think about water flowing down the river, and it, say, goes through a net that's submerged in the water, and you might ask how much water passes through the net in a given amount of time. So that's an example of flux. So here's what we're going to do in this slide. We're going to, or in this video, we're going to first think about a couple definitions that we need. Then we're going to think about how we should define flux in the simplest case, that is when we have a constant vector field and it's passing through a flat surface. Okay, once we have that, then we'll be able to use the very common strategy in calculus, which should start to be familiar by now, to give a formal definition of a flux integral. And then finally, we'll start to think about how we're going to calculate flux integrals in cases that aren't simple, that is where the vector field isn't constant or the surface isn't flat. So the first thing to do is think about a surface that's in 3 space, and the surface could point in 2 directions. It could point, this surface could say point to the right, or it could point to the left. And initially I just have to decide which way is going to be the orientation. So I'm always going to do that by picking one of the unit normal vectors that's normal to the surface, and do this in a consistent way. So for example, if I have a surface that's not flat, then everywhere on the surface I'll get a different normal vector, but I have to pick them in a consistent way. I don't want to pick some that point up and some that point down. And so that is the orientation of the surface. And these normal vectors, and we're going to think of these as unit normal vectors. Next, what we'll need is an area vector. So we're going to denote the area vector a vector. And first, I need to know what the orientation of the surface is. So we pick one of the directions of the surface to be the normal vector. Then the area vector A does 2 things. First of all, it points in the same direction as the orientation vector. And second, the magnitude of the area vector equals the area of the surface. And that's all there is to that. So here's the idea of flux. And again, the easiest way to picture this is to think about water. So think about water flowing through a rectangular surface. So the water is flowing through this rectangular surface, and it has a velocity vector of v. So this velocity vector doesn't necessarily, of course, have to be perpendicular to the rectangle. Okay, but there's the velocity vector. And what I'm going to do is I'm going to let the water flow through the surface for some unit period of time. Could be a minute or a second or an hour or whatever, it doesn't really matter. And then I collect all the water that passes through this surface in a given unit period of time, and I call the volume of water that's passed through the surface in that time the flux. Okay, if the velocity vector of the water is constant and the area vector is that of a flat surface, so this area vector is normal to this surface, and its magnitude represents the area, and I've chosen this particular orientation, then with a little bit of trigonometry, we can determine that the area, the volume of this shape, which is the volume of water that's passed through this surface, is simply equal to the magnitude of the rectangle that the water is passing through times v cosine theta, which is the height of this object. So So notice that what we get is the magnitude of A times the magnitude of V times the cosine of theta, where theta is the difference between the area vector and the velocity vector. But notice that that's exactly the definition of the dot product. So the flux then is simply equal to the area vector dotted with the velocity vector. Okay, so just keep in mind that this was the simplest case. Flat surface, constant vector field. So then, of course, the question is, what do you do if the surface isn't flat and the vector field isn't constant? Well, you do the same thing that you always do in calculus. You break up your surface into very small pieces. So these are the small pieces that I'm thinking about. And on each of those pieces, think about a tangent plane. So the surface is essentially flat. And if each piece is small enough, then the vector field is essentially constant on that piece. And so on this piece, we'll call this piece delta A. So that's that delta A. And if I dot that with the essentially constant vector field on that piece, I get the contribution of one of those small pieces. And then, so of course, what I'm going to do is I'm going to add all those contributions up and let the size of each of these small pieces get smaller and smaller and smaller. And in the limit, as that goes to 0, we get a flux integral. So a flux integral is simply an infinite contribution of fluxes on very nice surfaces, which are flat and the vector field is constant. Here's a first example. We'd like to find the flux of the vector field I minus j plus 3k through the triangular plate with vertices at 1, 0, 0, 0, 1, 0, and 0, 0, 1, and oriented away from the origin. So you'll see that this problem is really more of a high school geometry problem than a calculus problem, but let's go through it. So first I've drawn the triangular plate in 3 space, and let's indicate the orientation. So the orientation goes away from the origin, so that should point away from the origin. And notice 2 things. So the surface is certainly flat, it's a triangle, and the vector field is constant. So ultimately, my flux should simply be equal to, sorry, let me erase that. No, I can't erase it. The flux should be equal to the vector field F dotted with the area vector, because we're in the simplest case. So really the only problem is to find the area vector, because we have the vector field vector. So let's just do a little bit of geometry here. Notice that the vertices of this triangle are at 1, 1, 1. So the length of one side of the triangle, let's think about that. I have a triangle down here in the xy plane that's 1 along the x-axis, 1 along the y-axis. So the length of this hypotenuse down there is the square root of 2. So I'm going to record that down here. This length is the square root of 2. Okay, and this length, it's an equilateral triangle, so this length is also the square root of 2. So what I need to do is I need to find the height of this triangle in order to find the area of the triangle. So use Pythagorean's theorem again, and you'll find that that height y is equal to the square root of 3/2. Okay, so the area of this triangle is 1/2 base times height. So 1/2 times the base length, which is the square root of 2, times the height, which is the square root of 3 over 2. And so the area of the triangle is the square root of 3 over 2. Okay, so the next thing I need to do is I need to write down an area vector whose magnitude is this, the square root of 3 over 2, and whose direction is the same as this orientation vector. So look at the orientation vector, and I think that you can convince yourself that the vector is pointing in the direction I plus j plus k, but I need it to be a unit vector, mostly so that I can write down the a vector more conveniently. So I'm simply going to divide by the magnitude of that vector, which is the square root of 3. Okay, so finally, I'm ready to write down a. The a vector, the area vector, is equal to Well, it's pointing in the direction of the orientation unit vector, so it's pointing in the direction of I plus j plus k over the square root of 3, okay, but remember we want it to have a magnitude of the square root of 3 over 2. So I'm simply going to multiply that by the square root of 3 over 2. And notice conveniently the square root of 3's cancel, and we get 1/2 times I plus j plus k. So then, finally, the flux is simply the vector field F dotted with the area vector. So everything's constant, so this is easy enough to calculate. From the I components, we get 1/2. From the j components, we get minus 1/2. And from the k components, we get plus, oops, that was a minus 1/2, sorry, plus 3/2. So in the end, the flux is 3/2. Okay, so the second example is slightly more complicated. The vector field is not constant, but we want to find the flux through a flat surface, and that flat surface is the square. This square lives in the xy plane, and it has x values between 0 and 3, and y values between 0 and 3, and it's going to be oriented upward. So imagine the x-axis coming out of the screen. So there's xy, and the z-axis is coming out of the plane, and so this orientation is toward you. Okay. So first what we're going to need to do is think about the a vector. But in this case we're going to think about a delta a vector because the vector field is no longer constant. So delta a, notice that the delta a living in the xy plane has a delta x piece and a delta y piece, and its orientation is in the k direction. So delta a is delta x, delta y, that describes the little square, and its direction is pointing in the k direction. Okay, so that's delta a. So now, in the definition of the flux integral, we need to think about f dotted with this small flat piece where we can assume that the vector field is essentially constant. So what is this? Well, the vector field is xk, and we're going to dot that with delta x, delta y, k. And notice there aren't any i's and j's to worry about, but when we do the dot product we get a scalar valued expression, which is simply x, delta y. Now, as we add these all up, and we let the size of these delta a vectors go to 0, and add them all up, we get a flux integral. And the flux integral is the flux over this surface, which is the square, f dot dA, and what we get is an integral of this thing over the square. So we're going to do a double integral. The integrand is going to be x dx dy, where the y values go from 0 to 3, and so to the x values. Okay, this is a very simple integral to evaluate. It's a polynomial, and if you do that, you get 27/2.